Hello, everyone, and thank you all for joining us. The views, opinions, and technical analysis presented during this webinar are those of Ascend Performance Materials and are not necessarily those of UL. The appearance of this content on UL sites does not constitute an endorsement by UL or its affiliates. Today's webinar is Take the Heat. Starflam FR polyamides enable safer, higher voltage EV power systems, and it's presented by Ascend Performance Materials. Your presenters today are Dr. Kim White. Kim is a principal technology scientist and has 24 years of experience in the flame retardants industry. Since joining Ascend, she has focused on developing new flame retardant compounds for polyamides, including PA66 and specialty long chain and aromatic polyamides. And Kai Becker. Kai is the global application development leader for structural components and e-mobility. He focuses on identifying unmet market needs and translating these into new products and developments and launches. My name is Derek Becker with UL, and I'll be moderating today's webinar. Please send us your questions by typing them in the question box located on your screen. We're recording today's event, and we'll send you a link by email once it's been posted to ulprospector.com. Now I'd like to hand it off to Kim. Are you ready to begin?
Hi, I'm Kim White. Thank you all for joining our webinar today. I know we're all interested in facing the technical challenges of making electric vehicles and high voltage connectors safer. And so today I'm really excited to have this opportunity to introduce Ascend's new flame retardant product line for high voltage connectors in a variety of applications, including electric vehicles. And we do also have a second, more specialized design for thermal runaway protection in lithium-ion battery systems, which my colleague Kai Becker will present in the second half. So let's go ahead and begin. When we talk about flame retardant systems, we really like to open with discussing fire safety. Though there are still no regulations in automotive requiring certification for flame retardancy, OEMs and other companies realize the importance of making vehicles safer. In the diagram on the right, you'll see the stick figure running to escape the fire, and below its leading foot represents the early stages, the incipient stages of a fire. And flame retardants really only work during these early stages. Once the flame retardant spreads and leads to flashover and fire penetration, even the flame retardants no longer help. But a good flame retardant system will help delay ignition and spread of the fire and increase escape time by up to 4 to 5 minutes. On the left, we show a fire triangle, which shows the 3 components that are necessary to sustain a fire. If one interrupts any one of these contributors, you can extinguish a fire. And flame retardants operate by one or more mechanisms to interrupt the cycle. And then we have thermal runaway, where we require a specially designed system to contain a fire from penetrating outside of a battery pack. So when we started out with developing these products, we were faced with a variety of challenges and needs. And the first is high voltage insulation. In our case, would be the polyamide. And it's required to minimize voltage breakdown and provide insulation resistance. And it also has to perform at elevated temperatures over long periods of time. And it has to perform at high voltages, even exceeding the measured CTI of 600 volts. And CTI is comparative tracking index. We do know that groups are working on developing more realistic ways to measure tracking index at the higher voltages, but right now there's no established method in the industry. The next area is metal contact corrosion resistance. Again, must perform at high voltages and temperatures, as well as humidity. And one must take into account the flame retardant and heat stabilizer chemistry to help minimize the corrosion effects. The flame retardant orange color has also been adopted for high voltage connectors, and this signifies exposure to high currents and voltages. The REL 2003 is the one that is typically targeted, and it can achieve a UL 94V0 rating and has to retain color over temperature, time, and humidity, as well as maintain good flow and processability for a variety of connector types. And then lastly, we have thermal runaway resistance. This had to be considered where extreme temperature rises and pressure spikes are observed, and there's the need to delay the runaway spreading the fire as long as possible to increase escape time. Our first development can last about 2 minutes in this test, but we needed a more specialized design for longer delay times. And Kai Becker will cover in the second half a system that can last up to 15 minutes. Here we show the breadth of our Starflam 500 series portfolio. It's a non-halogenated product line with 2 heat stabilizer options. The 5 in the naming really just signifies glass fill PA66. The next number shows that we have a variety of different glass fiber offerings, from 15% to 25% and up to 35%. And then we have two heat stabilizer options. There's a K heat stabilizer, which is electrically neutral, and then also an H heat stabilizer, which is represented by a bound copper system. And normally you would not want to have a freely dissociating copper material in electrical connectors, but in this case, it's a specialized material that is complex to phosphorus, and it does not easily dissociate. And it's also not water soluble, so it can't dissolve in the water and migrate to the leads and cause a short. In addition, it's melt blendable, so you can have very small amounts that distribute very well during compounding. And then we show the color indicator, where we offer both natural black as well as orange. One of the most important characteristics for electrical connectors is that we have good thermal aging performance. And this is showing how our both K and H heat stabilizer grades compare to competitor products. Relative temperature index is a reflection of the maximum temperature where a property will not be unacceptably compromised. And this typically means that the point of failure is around 50% of what the original value, unaged value is. It's also measured relative to a reference material, so one has to select a reference material carefully, and it will have already a confirmed corresponding RTI. So in automotive, they don't have a requirement here, but if a material carries an RTI certification, then the automotive customers can feel confident that it'll perform well. And then it's required for a variety of other electrical connectors. What we can see here is there's three different types of RTI values. There's electrical, which is based on dielectric strength, impact strength, and then strength, which is the tensile strength. And we can see that our K grade performs very well compared to the competitor materials, and our H grade even better, achieving best in class, especially in the RTI electrical, which is the primary RTI value that our customers have requested. Metal contact corrosion is also an important characteristic, and you can see a corroded connector there on the left. The test that we do is an IEC method, and it's for 10 days at a given selected voltage, so you can only run one voltage at a time, and it's done at 55 degrees and 93% relative humidity. In the diagram there, you can see that we can test 5 samples at a time, and there are cylindrical tubes that are holding the polyamide compounded plates. So the dash shaded material there that you see is being pressed against a metal strip. And you can look at the detailed view and see how that tensile bar is being pressed against the metal strip. And it's the metal strip that is evaluated both qualitatively and quantitatively. And here shows the classification criteria. So qualitatively, both the anode and cathode sides of the metal strip are evaluated, and you can see they can be classified anywhere from non-corrosive to slightly corrosive, or even strongly corrosive. And then there's also a K factor, which is the quantitative aspect in the column second from the right, and this is represented by how much the tensile strength of that metal strip diminishes after heat aging versus its initial unaged value. For both of our heat stabilizer grades, we're able to achieve an A2K2 grading, which is slightly corrosive. And this is comparable to competitor materials in the same class. And here we show a product selector, and how would you decide if you would want to use the K or the H grade. In the chart on the left, we can see the K factors at lower voltages are very comparable. But as we go to higher voltages, we consistently saw lower K factor values, so lower loss in tensile strength after aging for the K grade. And so we like to designate the K grade for higher voltage applications, but the H grade, as we showed you before, with the RTI values being much higher, there's an advantage for applications that require that, as well as the H grade exhibits lower smoke density that satisfies the European rail requirements. And it can satisfy interior requirements of R22 HL3, as well as the exterior. Now, something important to molders is not having to shut the molding machines down when they're processing a given material. And usually they like to be able to run at least 2 weeks without having to shut down. And here we show a spiral flow length and the y-axis as a function of moisture. And looking at competitor product A, it has a very high flow, but a very steep curve response to moisture. So it might be a little bit difficult to dial in the molding conditions with varying moisture. And then if we look at product C, it's got a very flat curve, so it's not responding a lot to moisture, but then its flow is not very good. We view our Starflam 500 series as being a balance between having high flow and lower response to moisture. Another aspect that molders care about is plate out. And this relates to how much residue can get stuck in the vent lines. And basically what we do is we weigh the amount of material that's caught into the vent lines, and we dissolve it in methanol and then evaporate it and measure how much material was accumulated. And this is done over 1,000 shots. And we can see that our 525 grade exhibits much lower play out versus competitor products A and B. And then we talked about the orange RAL 2003 that we like to target for this application. And if you look at the diagram on the left and that red square in the middle, that would represent the RAL 2003. And after aging over time, you can see that going into the green space, it would move very far from the RAL 2003. Versus if we start a slightly shifted value and then age 500 hours to that red dot and then 1,000 hours to that red dot, we end up in a place that's closer to the targeted RAL 2003. And looking at the middle section, we can see the driest molded color as well as the 500-hour aged and the 1,000-hour aged. And then all the way to the right, we actually have a laser markable part, and that shows laser marking done with UV, ultraviolet. And here we show the breadth of our glass fiber loadings. So we have anywhere from 15% to 25 and 35%. In the middle column is our workhorse product, the 25% grade, which applies to the majority of applications, including high voltage circuit breakers, relays, high voltage switchers, and sensors. But if somebody's looking for like higher elongation, a little bit more ductility, the 15% grade would be the better choice. And this is useful for industrial connectors, as well as folks like to use the H grade there where they require a little bit better thermal stability. And then all the way to the right, we show the 35%. This is useful for applications where they require higher strength. And you can see that reflected in a higher tensile strength value. And that's useful for industrial power management devices, as well as manual service disconnect and pyrotechnic battery disconnect. And this is a summary showing how our product compares to the competing products A and B. This is a spider diagram, and the best performance are values that are on the outside of the spider diagram, whether they're high or low numbers. We reflect that as being better on the outside of the diagram. And this is showing that we achieve thin part ratings for flammability and RTIs for better design flexibility. We could get V0 down to 0.2 millimeters, as well as 5VA at 1.5 millimeters. And our RTI electrical actually spans 0.2 to 3, which is very broad compared to most of the competitor materials. We also show efficient molding as reflected in the plate out behavior and the flow. And then also improved ductility reflected in the elongation, especially for the 15% glass fiber. And also we exhibit low metal contact corrosion, and these materials are recyclable with a 50% regrind rating. And they are European REACH and ROS compliant. So this concludes our first half describing our 500 series product family for a variety of high voltage electrical connectors. We will now segue over to our second half, where my colleague Kai Becker will describe a more specialized design for thermal runaway protection in lithium-ion battery systems.
Thank you, Kim, for that segue. Hello, everyone. Also welcome from my side to our webinar. This is Kai Becker speaking, and I'll talk you through a few pages about what we can do with thermal runaway exposure onto our thermoplastic materials. So we all know this is a major challenge, especially when we are talking about the use of lithium-ion technology, but there has been a lot of progress made, right? So today we have really sophisticated battery management systems. We also have advanced disconnect units, and we have built as an industry a lot of experience also about pack design that can deal with thermal management, barriers, but also vents for regular operation and thermal runaway. And of course, in the meantime, we understand through various performance tests that have been established how to rate and rank material options and also technology options. Last but not least, of course, this is a question which material solutions we also have at our choice. And I want to present one of those material solutions out of our portfolio today. So the material that we want to talk about is called Starflam X Protect. And well, from a processor side, this is how it would work. We ship and deliver a ready-to-use compound that you can use to mold your injection molded parts. And it processes like you are used to operate with a polyamide 6,6 base material. Then the molded parts need to undergo a secondary operation. And after this exposure, the parts or components will be ready for assembly, both for component level and of course also for vehicle level. Now, on the right-hand side, we explain a little bit what that formulated compound together with the secondary operation does with the material. We're looking at a plot of the dynamic modulus measured in a dynamic mechanical analysis, or DMA, and we plot this modulus over the temperature. And the green dotted line shows the behavior of a regular flame retardant PA66, unreinforced in this case. So we start with a modulus of about 1000 megapascal. We're losing a little bit of that modulus as we go through glass transition temperature around 50, 60 degrees C. And then we see a very significant drop of that stiffness as we approach the melting point, even to the extent that we can't measure a mechanical stiffness anymore at around 230 degrees C. The formulated polymer with X-Protect technology and gone through that secondary operation follows the red solid line. We start at a very similar level and we see the same physical effects of a regular PA66. So some softening throughout the glass transition temperature, a loss of rigidity as we approach the melting point. But then at a certain temperature level, we maintain a storage modulus of around 7 to 8 megapascal, even clearly past the melting point. Now, this is how far we can take it with the DMA method. But in the following couple of minutes, we want to show you a video that highlights what the material does when we're exposing it to thermal runaway conditions. Yes, here we go. So what we did is we tested a few materials in a torch exposure. The torch in this case was a serious burner, so 1.4 kilowatt power and 1100 degrees C calibrated temperature. And we're comparing an automotive grade aluminum, a regular flame retardant glass fiber reinforced PA66 in the middle, and Starflam X Protect on the right hand side. Both PA66 grades are glass fiber reinforced and all samples have 3 millimeter thickness. So in the beginning, we see a little bit of buckling on the thermoplastic parts due to thermal elongation. But then the next development that we observe is a melting of the regular PA66 and the rupture of the plaque within 2 minutes, 20 seconds roughly. The same is happening to the aluminum plaque. Just a little later, we have higher melting point, more heat capacity. So we need a little more time at that thermal power to heat through the aluminum, but we are able to rupture this within 4 minutes. And on the right-hand side, we're looking at Starflam X Protect, that after that initial buckling really doesn't change anymore. So the flame keeps burning, as you see in that IR picture, and the plaque withstands this exposure throughout 15 minutes, which is this timestamp where the lab decides that they would prefer to shut down the burner for their safety protocol. So based on this test, and this is the power plant fire penetration test, Starflam X Protect can be rated fireproof. So if we go back to our presentation after this video, we'll give you a little bit of guidance on how to select that material. We've seen this torch test, and so if we approach this question of material selection in a field of exposure, temperature, and time, there are a few simple questions that you could ask. The first one is, does your component need to operate above the polymer's melting point. So for PA66, this would be 265 degrees C. If the answer is no, then you're probably good with a regular Starflam flame retardant material. If the answer is yes, the next question would be, for how much time do you need to be at that temperature? If this is a very short exposure time, say 1 to 2 minutes, and referring to that video, within 1 to 2 minutes, we might be able to sustain this with a regular flame retardant material. If you have really long exposure time above the melting point of the resin, this is the area where Starflam X Protect really can play its strength and has a fit. Hence, the last question is to compare it against other technologies, and other technologies could be to protect your component with separate additional components. And you've got to compare, of course, the cost situation against a one-shot solution like Starflam X Protect. Now, with this decision-making framework, we'll take it to some application examples. And the first one that we want to bring to your attention is the use of the material as an insulation function. So think about, for example, an overmolded bus bar that is used for the module-to-module connection inside your battery pack. And the requirement is, of course, a certain performance of the electrical insulation throughout the regular operation. But the expectation is also to maintain the electrical insulation for a certain period of time throughout a thermal runaway event. Of course, if you would use, if you would use a regular flame retardant PA66 and expose it to temperatures above your melting point, you would exhibit that bar after a very short period of time, like 2 minutes or so. The insulation layer would burn and melt away and expose the bar, which is a failure with regards to the ask. Starflam X Protect, in this case, we were able to expose it to a flame of 800 degrees C for 25 minutes. And after these 25 minutes, still the bar performed with the proper electrical insulation properties that you would expect from the virgin component. Another application example is of barrier functions. So think about your pack design. In modern packs, we're seeing more and more that modules are no longer separately enclosed. In this cell-to-pack approach, we still want to have a certain segmentation of the battery pack in different modules, but we talk about module bays that are a design feature of your housing, and we want to still have a barrier between the module bays. So in case of a thermal event, this event does not propagate from one module bay to the next. So these barriers can be produced, for example, out of Starflam X Protect, and we already went through some successful component level tests. That means we have barriers produced, exposed them to a torch. And from our perspective, the next level of testing would be to go to an actual pack and see whether that propagation can be really stopped. So this is also a matter of thermal transition and heat transition. I'm really looking forward to those kind of testings. This kind of concludes what we were presenting today about thermal runaway as such. Just to give you an overview of the tests that we already did, and we understand how our material performs. We participated in a project of AZL in Germany that was developing a test device that measures mechanical properties at thermal runaway conditions. So you see these clamps in the left-hand picture that grip the specimen and the burner underneath. It's really to generate stress strain data while the component is at these 800 degrees C, for example. We also ran this power plant fire penetration test at the lab Aeroblaze, and this is the video that you have seen before. We ran the UL2596 tests, only still need to review data and summarize the results, and we will gladly keep you updated in the future about that outcome. And we also ran a particle blast testing known from some laboratories as torch and grit, for example. And we managed to pass 2 entire cycles that consisted out of 30 seconds flame dwell and 20 seconds grit blast. With this, we conclude really what we have about thermal runaway, but I also want to give you some hints how you could use X-Protect in a different context that still can be automotive, but doesn't necessarily come with these extreme temperatures. So another application space can be in the context of reflow soldering. Think about a cable to board connector and the board connections of electrical components or electronic components, and that connector are generated by reflow soldering. You want your molded connector to withstand this reflow soldering temperature level throughout a time of 10, 15, 20 minutes, depending on how you establish your solder process, without, first of all, deformation. But even more critical for polyamides, you don't want to generate any blisters. There is this standard called JEDEC, JSTD 020, where materials are rated by their moisture sensitivity level, or MSL. And MSL1 is basically the best performance you can achieve, where a component can be stored under humid conditions and still not exhibit any blisters when going through the reflow solder process. Starflam X-Protect achieves that level compared to regular PA66 type of materials. And other materials that can achieve that level would be PPA or PPS. Another application space is in the production of enclosures for circuit breakers. Especially in North America, these enclosures are primarily produced in thermoset. With X-Protect technology, we can produce those housings and perform really good in what they call the high voltage, low current arc resistance according ASTM, which is shown in the right-hand side picture. It's a bit comparable to CTI, only the voltage is higher and you don't need any electrolyte to run the test. This is due to the fact then that when switching those circuit breakers, you might generate an arc in the switching chamber. And of course, that arc should not generate or lead to any harm of the enclosure or compromise even the function of the enclosure. If you look outside of the US or North America, you would also see requirements like a fire test that simulates a fire inside that circuit breaker box, where those circuit breakers would be installed. And of course, the requirement is that the circuit breaker housing is not compromised in its shape or in its insulation function. And any thermoplastic material, be it flame retardant or not, would certainly deform and deflect and lose its structural integrity under that fire exposure. Not so Starflam X-Protect. So with these two performances, we are able to perform properly in circuit breaker housings. That can be also a thermoset replacement in some areas of this world. This last page really takes us to the end of our presentation. So thanks already a lot for your attention. And before we go to the question and answers, I quickly want to summarize that while we understand that today there are new challenges coming with the electrification of the vehicle powertrain, that comes with new requirements for safety and performance. We feel confident that with Starflam and Starflam X-Protect as material family, we have the material that helps our customers and you to design for safety without sacrificing performance. And in addition to the material that we provide, we also have our own expertise about the industry and, of course, about our materials that helps our customers to get faster to market with a good solution or even the best solution. With this, I'd really like to thank you for all the attention, and we're getting started with our question and answer session. Thank you again.
Excellent. Thank you, Kai. We have had quite a few questions come in, and just as a reminder, please use that questions tab in the bottom right-hand corner of your screen and submit your questions as we continue along. First question we have here is, how does XProtect compare to PPA?
Yes, thank you, Derek. So think about as XProtect being based on PA66. So if you process the material and produce your injection molded part, you have the ease of processing like a PA66 material. But then leveraging and initiating the XProtect technology that takes literally the melting point away, we can, of course, have clearly higher performance, as we've also seen in the pictures about the circuit breaker housing, than a PPA. So comparing those directly is we can process better than PPA, and we also outperform on component level.
Is XProtect recyclable?
Yes. That's really a tricky question because, well, since we claim to take the melting point away, one would expect that you cannot really recycle it. But remember that DMA plot where we talked about the level of modulus that we retain after the melting point. This is strong enough to provide some structural integrity even past the melting point, but also soft enough that we can shear it in a melt processable device like an injection machine and blend it with virgin material. So yes, it is recyclable.
Does 525 match RAL 2003 dry as molded?
So in the sense of the color requirement in automotive to signalize high voltage content, I would say yes. The requirement is pretty broad. It says recognizable orange. If you recall what Kim had presented with this transition throughout the color space, we deliberately picked an origin before we go through a color shift throughout heat aging that is not spot on with RAL 2003, but makes sure that throughout the heat aging, we stay as close as possible to RAL 2003. So it's not as close as we can go, but then we retain the better proximity throughout the heat aging period. So I still would answer your question with a yes.
And is it available globally?
This was actually one of the biggest challenges, to be honest, in the development of the orange version, to find a pigment chemistry that is registered in the main regions and that we can use in the main regions. And we managed that for this 525K orange. So it's going to be available globally out of our production sites in Europe, in France, in Suzhou, in China, but also in North America and Fort Lee, Alabama.
Yes, and we do also have the natural and black versions available for the 25% glass filled and the 15% glass filled, and we will soon have samples of the 35% glass filled available.
Excellent. And then, Kim, here's a question for you. Is salt spray test done for corrosion testing as well?
The salt spray test could be done potentially by the tiers or the OEMs, but in the sense of what we were going after here, it's really trying to go after the metal contact corrosion resistance driven by the presence of electricity in the system, not so much like external salts exposure.
And then a question for Kai. What is the product life of Starflam for electric vehicle after molding?
That's a complex question. So we've seen the RTI data that Kim had presented, and that's essentially one of the main degradation mechanisms that we would see throughout an automotive lifetime that is based on heat aging, which is actually what the RTI is rating. Keep in mind that RTI describes the temperature that degrades your properties down to 50% after an exposure of 20,000 hours. So thinking about the lifetime of an electric vehicle, considering that it's not just the drive cycle that we need to assess. So in the past, automotive companies have been looking at heat aging data for, say, 3,000, maybe 5,000 hours. For electric vehicles, we also need to add the charging cycle to that heat exposure. So let's say roughly double the drive cycle time. We believe that with RTI 20,000 hours, we're really safe on that side. knowing that RTI is more an electronic industry metric, not so much common yet in automotive. But we're happy to go more in detail when we know the component and the exposure temperatures, and then assess how well we do and how well we retain properties. But overall, we are confident that Starflam is fit for the automotive use.
And then here's a question for either of you. Are these products halogenated?
Yeah, for the 500 series, they are non-halogenated. And then Kai, for the X-Protect?
The same, yes. We're using non-halogenated constituents and additives.
Great. And then a question for Kai. Does X-Protect have 5VA performance?
It does, but I have to admit that I don't know the thickness level straight from the top of my head. So we can gladly connect at a later stage and provide you that information. You can also consult UL Prospector and look for the yellow card of X-Protect technology materials, or look at our data sheet on the homepage that should carry some flammability data as well.
And then Kai, another question for you. Is X-Protect tested for glow wire? Are there plans for an unfilled grade?
I take the second part first. We have a portfolio of commercial materials active today, and that consists of several grades that are both flame retardant and not flame retardant, but also glass fiber reinforced and not glass fiber reinforced. So we have unreinforced versions already today, both flame retardant and not. With regards to glow wire, I would believe we have glow wire testing already, but I would be happy to discuss the requirement level. So is this a requirement coming, say, from the unintended appliance side, or is this something related to automotive? Would be specifically interested if it was for automotive, because we don't see a lot of glow wire yet, but we believe that's coming and it's going to get more. So I'd love to take that point further. But I also am confident that it would operate quite nicely, specifically if we talk about a flame retardant version that also suppresses the fire in parallel with that X-Protect technology.
And then a question for Kim. Are there different grades of Starflam 525 material resistant to UV rays, extreme environment conditions suitable for IP67?
Yeah, I'm not sure about that IP number. We'll have to look that one up later, but we do have an F1 rating for our 525K.
And then Kai, how does X-Protect behave under a particle blast? On
one of the slides of the presentation, and click back to that page, we already talk about that particle blast. So we ran particle blast and flame dwell in a slightly different cycle that you might be used from other test laboratories. So we used 30 seconds flame dwell and 20 seconds grid blast. And in this exposure, we are passing 2 entire cycles with X-Protect injection molded material in a 3 millimeter thickness substrate.
And then can we use Starflam for water cooling manifolds of truck engines? And can we do blow molding of Starflam for ducts near engine from metal to plastic replacement?
In terms of the 500 series, I am not sure about that. We designed these for electrical connectors. I guess folks are welcome to try them in those other applications, but I'm not sure. And for the X-Protect, Kai?
So overall, X-Protect helps also the chemical resistance. So I would, on a broad basis, I would say that probably both could be used for coolant connectors or coolant carrying parts. Maybe X-Protect is slightly better. What probably is the bigger factor is the formulation of those materials having glass fiber, but also a reasonable quantity of flame retardant additive So the ductility level that we start off with those flame retardant materials is slightly lower than not flame retardant PA66. And that's the first property that goes down or decreases when you expose it to coolant. But I wouldn't see why you can't use this. Probably not as a drop-in on a one-on-one offset against a non-FR version, but with proper design, I'm sure we can make it work.
And that's all the time for questions that we had. Thank you for attending today's webinar. Just as a reminder, we will send you a link to the recording of today's webinar so you can watch it at any time and share it with others at your company. We will also follow up to the questions that weren't answered. Now you will be redirected to Ascen's website for more information. Thank you again for attending and have a great day.